When I first saw the initial observation log, it looked ordinary. Another dim object, another routine detection. But there was something about the numbers that unsettled me before I even understood why. A fragment of data that didn't match the pattern, as if the sky had quietly slipped in something that wasn't meant to be found. The discovery itself was straightforward. On July 1st, 2025, the Atlas Telescope Network registered a faint point of light that hadn't been there earlier that night. Normally, this would signal a new long period comet drifting in from the Oort cloud. But when the orbital calculations came back, nothing aligned with that assumption. The path wasn't closed. It wasn't even curved in the way a solar-bound object should behave. It was hyperbolic, the unmistakable signature of something not born in our system. That's when the designation 3I Atlas appeared, the third confirmed interstellar object humanity has ever recorded. And even before we understood its chemistry, the trajectory already carried a quiet implication. It came from elsewhere. It was never coming back. I kept reviewing the early photometric data, expecting the usual slow brightening as it moved inward. Instead, what I saw troubled me. The object was active far too soon. At 3 astronomical units from the Sun, where water ice should remain locked and inert, sensors picked up an enormous outflow. Dozens of kilograms of water per second. A torrent, not a trace. At that distance, sunlight simply cannot supply enough energy for such behavior. Any comet physicist will tell you that. And yet the signature was undeniably real. Some of my colleagues whispered that the readings were miscalibrated. Others raised a more delicate concern, that we may have been seeing surface activity driven by something other than water ice. I remember a quiet remark during a late-night data review, someone saying that the energy balance felt artificial, though no one dared expand on that. The official explanation came later. Carbon dioxide, not just present but overwhelmingly dominant in quantities no comet from our own system has ever shown. 8 parts CO2 to 1 part water, a ratio so extreme that it implies a formation environment entirely unlike anything near our sun. Colder, darker, richer in volatiles, the kind of place our models do not typically account for. And yet this object carried that chemical fingerprint with absolute clarity. If that had been the only anomaly, it would have been enough. But the age estimate changed everything. By backtracking its trajectory and measuring the degree of cosmic ray weathering on its surface, the teams arrived at a number that left even seasoned astronomers in silence, somewhere between 7 and 10 billion years. Older than the Earth, older than the Sun, formed in a galaxy that was still young and turbulent. Several observers privately admitted that they struggled with the implication. A body that predates our solar system by billions of years, arriving now by chance at the one moment in human history when we have the technology to detect it. Coincidence, perhaps, or simply the scale of cosmic time dwarfing our intuition. As more observatories joined the effort, ground-based telescopes, spaceborne instruments, ultraviolet detectors, we began assembling a portrait of a visitor unlike any we had seen. Not a silent rock like Oumuamua, not a familiar water-dominated comet like Borisov. Something older, more volatile, chemically alien, and yet some details refused to settle. Short-lived radar signatures that appeared and vanished. A set of ultraviolet readings temporarily restricted before being reissued in revised form. Small things, each with logical explanations. Instrument noise, calibration errors, routine data handling. But I've learned that sometimes the smallest inconsistencies are the ones that linger longest in the mind. For now, the object continues inward, shedding material it has preserved for nearly 10 billion years. We can observe, we can measure, but the deeper story, the world it formed in, the star that once warmed it, is beyond our reach. That system may not even exist anymore. I can't yet say what the next phase of this investigation will reveal. But the closer I look, the more this ancient traveler challenges the comfort of what we think we know. Whether it's just a rare chemical outlier or something that hints at a broader galactic pattern, that's a conclusion I'm not ready to make. Not yet. I kept thinking about that early surge of activity, the water escaping where no water should. It felt like a clue we weren't yet equipped to interpret. And as the object drew closer, the instruments we relied on grew sharper, as if the sky itself was urging us to look deeper. The first real answers came from the spectroscopy teams. Their work is meticulous, almost forensic, breaking light into colors, searching for molecular fingerprints hidden in the faint glow surrounding the object. At that time, 3I Atlas was still dim, too dim for most telescopes to handle. But the global network didn't hesitate. One after another, observatories across Earth turned their mirrors toward the visitor, collecting every photon it offered. It wasn't enough. So the call went out to space. I remember the moment the first JWST readings were circulated internally. The infrared spectrum was unusually clean, almost unnervingly so, dominated by signatures we don't often see at that strength. Hubble confirmed a broad, expanding coma that didn't match the expected geometry, and several ground-based teams reported dust jets whose symmetry seemed off. Not wrong, just unfamiliar, as if the pressure beneath the surface was behaving differently from anything in our catalogs, but it was the ultraviolet detectors aboard the Swift Observatory that delivered the decisive blow. A bright hydroxyl signature, far brighter than any reasonable model predicted, revealed not only the presence of water vapor, but the sheer scale of it, and behind it, hiding in the spectral noise, was a pattern that hinted at another driver entirely. When the chemical ratios were finally published, they read almost like a transcription error. CO2 wasn't just present, it dominated. The measurements placed it at nearly 8 times the abundance of water, a ratio so extreme that it forced us to redraw the entire formation scenario. Water-rich comets are ordinary here, but carbon-rich, water-poor bodies, those hint at a birth environment colder and darker than anything in the outer regions of our own system. Some researchers quietly noted that such a composition isn't just unusual, it's alien in the strict chemical sense, a product of a disk with different temperature gradients, different frost lines, and perhaps a completely different stellar radiation history. And although no one said it outright, there was a growing recognition. Whatever system birthed 3I Atlas did not resemble our own. That idea lingered with me more than I expected. There was a second mystery as well, one harder to quantify. Several observatories reported inconsistencies in the earliest spectral datasets. A few emission lines appeared briefly and vanished on subsequent exposures. One set of raw files was flagged for internal review, then quietly replaced with a revised version hours later. Officially, it was a calibration correction. Unofficially, a few colleagues admitted they'd never seen a correction handled that quickly. Perhaps it was nothing. Yet most unanswered questions begin exactly that way. The assembled chemical profile nevertheless painted a startling picture. An object coated in volatile carbon dioxide, capable of erupting violently even under weak sunlight, shedding water ice not through heating but through mechanical ejection. A system powered not by slow sublimation but by buried reservoirs of supervolatiles cracking open under pressure. A comet that behaves more like a geyser than a melting snowball, and if that was true, it meant the object wasn't merely old, it was primordial, preserved under conditions that allowed its chemistry to remain frozen for longer than the lifetime of our sun, a fragment of a world whose star may already have died. I found myself returning to the decrypted data again and again, searching for patterns in the noise, anything that might hint at the environment that shaped this thing. But every time I thought I was close to an answer, another piece of evidence unsettled the picture. One astronomer, speaking strictly off record, mentioned an unusual infrared slope that didn't match any known grain distribution. Another hinted that certain models failed unless the nucleus was assumed to have internal layering far sharper than what typical comet formation would produce. And there was the quiet speculation, not public, never written, that perhaps we were looking at a relic from a region of space we hardly understand. A product not just of another star, but of another era. What troubled me most wasn't the chemistry itself. It was the implication that we were decoding the last surviving trace of a system long erased from the galaxy. A chemical fingerprint from a ghost star, preserved inside a body that had wandered billions of years through darkness. And yet this was only the beginning, because the closer we looked, the more the object refused to behave like anything familiar. What happened when we examined its structure in detail? That's the part I still struggle to explain. I kept turning over the same thought. If the chemistry was already unlike anything we knew, then its structure might hold the real key. But nothing prepared me for how fragmented and contradictory the structural data would become once the full observational campaign was underway. In the aftermath of the CO2 revelation, the global effort intensified. Every major observatory capable of tracking a faint, fast-moving object was brought into the fold. Not out of excitement, but urgency. 3II Atlas was accelerating outward on a path that left us little time, and as its brightness fluctuated, the inconsistencies grew sharper. Hubble's imaging came first. Its ultraviolet view revealed a coma expanding in a pattern that didn't match a uniform, spherical nucleus. Instead, it showed narrow plumes angled in ways that suggested deep internal fissures, fault-like structures rather than the shallow vents we usually see on comets. Some jets appeared and vanished within hours, as though the internal pressure was shifting unpredictably. Then JWST delivered its own contribution. Its infrared instruments detected thermal gradients steep enough to imply that some parts of the nucleus were absorbing heat far more efficiently than others, but that shouldn't have been possible at such distance. For a time, the leading hypothesis was surface layering, with ancient material overlain by younger, more processed crust. But that explanation collapsed when the thermal data from subsequent exposures failed to match the model. The object was rotating, shedding material, but the patterns weren't repeating. Something inside it was evolving even as we watched. Spherex deepened the puzzle further. Its spectroscopic sweep revealed faint bands that suggested an unexpectedly complex distribution of carbon-bearing molecules, not in the coma, but deeper within the nucleus. The readings were marginal and noisy, and yet they pointed to a compositional gradient sharper than anything produced by ordinary accretion. A few colleagues quietly floated the possibility that the nucleus had once been partially melted or altered by an intense event in its home system. Others argued that cosmic ray exposure over billions of years could produce strange stratification. No model fit comfortably. And then came the strangest set of observations, the ones that still trouble me. For reasons that were never fully explained, the European Space Agency authorized 2 spacecraft in Mars orbit to attempt long-distance imaging of the object. Mars Express and the Trace Gas Orbiter were not designed for deep space astronomy. Their optics were optimized for mapping a bright planet at close range. Turning them outward was little more than a technical experiment, but somehow, improbably, it worked. Both spacecraft returned faint images, only a handful of pixels, indistinct, almost lost in noise. But after careful processing, they revealed a shape that didn't quite match the Earth-based reconstructions. From Mars's vantage point, the coma appeared asymmetrical in a way that suggested additional jets or mass loss not visible from Earth. One analyst even proposed that a small fragment might have separated from the main nucleus, an idea swiftly dismissed, though privately debated. The 2 vantage point data created a stereoscopic baseline. When the teams combined the Earth and Mars perspectives, they noticed subtle shifts in the coma geometry, shifts that implied a complex internal structure, perhaps consisting of multiple pockets of trapped volatile material beneath an uneven crust. But one detail in the combined reconstruction stood out. The primary jet appeared to originate from a region far smaller than expected, a vent narrower than any seen on a comet of that size, narrower and deeper. When I asked a colleague about the depth estimates, he avoided answering directly. Instead, he sent me a plot with the cryptic note, "If this is accurate, we need to rethink the internal pressure models entirely." Another researcher mentioned off the record that several data points from the earliest Mars Express attempts were flagged and withheld from public release, officially because of low quality, unofficially because they contained anomalies not consistent with the instrument's configuration. I never saw those frames myself. I don't know whether they were simply corrupted or whether they hinted at something else, something still unresolved. But even without them, the overall picture was reshaping itself. 3I, Atlas, was no uniform body. Its crust was fractured, its internal volatiles unevenly distributed, and its outgassing behavior almost episodic. The more data we collected, the less it resembled a traditional comet. It felt like we were observing not a single object, but the remnants of something older and more complex, a frozen relic in the slow process of revealing its hidden layers. And yet the deeper we dug, the more elusive the truth became. With every new observation, the timeline tightened, as though the object itself was slipping out of reach. Because what happened next, when we attempted to model its evolution and future trajectory, introduced questions none of us expected. I kept waiting for the models to settle, expecting the simulations to converge the way they always do when enough data accumulates. But with 3I Atlas, every refinement made the picture less stable, not more. It was as if the object resisted classification, shifting just beyond the edge of our certainty each time we thought we understood it. The first major inconsistency appeared when the trajectory teams ran long-term projections. Hyperbolic objects usually behave predictably. Gravity bends them once, and then they fade outward along a clean mathematical arc. But 3I Atlas showed subtle deviations, tiny yet persistent, that couldn't be explained by the usual suspects. Not solar radiation pressure, not asymmetric outgassing, not observational error. I remember asking one of the team leads how confident he was in the anomaly. He hesitated before answering. "Confident enough to be uncomfortable," he said. Later, in private, he admitted that several early tracking datasets looked too neat, as if someone had already smoothed the noise before they reached the analysis teams. Whether the smoothing was automated or deliberate, no one could say. The deeper we looked, the more urgent everything felt. We were losing time. The comet was receding faster than we could adapt our instruments, and as the coma thinned, the internal jets weakened, making the structural features harder to detect. The sense of a closing window hung over every meeting. That raised the inevitable question: could we intercept it? Could we meet this 10-billion-year-old traveler face to face? The short answer was painful. No. The long answer was worse. To rendezvous with an interstellar object, a spacecraft must not simply reach it, it must match its velocity. And 3I Atlas was moving at over 200,000 kilometers per hour relative to the Sun. No chemical rocket humanity has ever built could deliver the delta V needed for a direct intercept. Even the fastest probe we've launched, New Horizons, would be left behind almost instantly. Ion drives offered theoretical hope, but only in scenarios with years of continuous acceleration. We did not have years, we barely had months. By the time the object was identified as interstellar, it was already deep into its passage, already turning outward. The choice had been made for us before we even knew it existed. A few speculative proposals circulated: high-energy trajectories, solar obirth maneuvers, even exotic propulsion concepts not ready for engineering reality. None survived serious analysis. One internal report, never published, concluded that an intercept mission would require a launch window that occurred approximately 2 decades before the object's discovery. In other words, impossible. That's when the discussion shifted to prevention, not of the comet, but of the situation repeating itself. If we couldn't chase 3I Atlas, perhaps we could be ready for the next visitor. This idea wasn't new, but the urgency behind it was. And so, a word began to reappear in every planning document: interception. Not as a response, but as a standing capability. A spacecraft launched long before a target is known, waiting in deep space like a coiled spring. Europe's upcoming mission, Comet Interceptor, suddenly felt prophetic. A probe that would launch without a destination, park at the Sun-Earth L2 point, and wait. When a pristine comet or an interstellar visitor was detected, it could ignite its engines and pursue, using the luxury of time, the one resource we didn't have now. I remember reading the mission architecture with a quiet sense of inevitability: 3 spacecraft working in formation, multi-angle imaging, close-range dust sampling, a design shaped not by theory but by the hard lessons of our failure to reach 3I Atlas. Several agencies began drafting their own concepts: nuclear thermal propulsion, solar sail accelerators, high-impulse stages. Ideas once considered academic suddenly felt necessary. Even then, a harsh truth undercut every proposal. We were planning for the next visitor while still struggling to understand the one already here. And yet the most unsettling issue was not technological, it was conceptual. Because as the final trajectory models for 3I Atlas were released, a strange detail surfaced. The non-gravitational accelerations were fading, but not linearly. The decline followed an irregular pattern, inconsistent with standard volatile depletion. Some observers suggested hidden CO2 pockets, others blamed rotation, a few hinted at model limitations. But one analysis buried in supplemental material posed a different possibility. The object's internal activity might have been triggered by encountering sunlight for the first time in billions of years, and now that it was leaving, it was descending into silence again, returning to the state it had held since before our solar system existed. If true, then everything we saw, every jet, every plume, every spectral line, was a brief awakening in an otherwise eternal sleep. A one-time event. Something we would never witness again. That idea followed me for days. It made the data feel heavier, as if we were not just observing an object, but interrupting a story far older than our species. And as 3I Atlas began fading into the outer darkness, the last glimmers of ultraviolet emission dwindling frame by frame, the models finally converged on the only certain outcome: we would lose it. Forever. And yet, in its final weeks of detectability, the comet revealed something else, something that forced us to rethink not just its nature, but our own assumptions about these interstellar visitors. I kept reviewing the final measurements, hoping for a pattern that would tie everything together before the object faded completely. But instead of clarity, the last weeks of observation brought the most puzzling data of all: subtle, easily missed, and impossible to explain cleanly. The first hint appeared in the ultraviolet logs. As the comet moved outward and its CO2-driven jets weakened, the hydroxyl signature associated with water should have diminished smoothly. Instead, it fluctuated. Not dramatically, just enough to raise questions. One emission peak rose briefly over a 2-hour interval, then collapsed again, long after the internal pressure should have stabilized. A few colleagues dismissed it as instrument noise. Others noted that it coincided with a short-lived spike in faint dust density recorded by a separate ground station. When I compared the datasets, I noticed something else: a minor delay between the dust increase and the UV response. It shouldn't have meant anything, and yet it felt like a reminder that the object's internal structure still held layers we hadn't deciphered. Deep pockets of volatile material arranged in ways our models couldn't map. Then came the final thermal readings from JWST. They showed a cooling curve that didn't align with any known pattern of surface conductivity. Some sections of the nucleus cooled rapidly as expected, but one region remained warm longer than it should have, even after correcting for solar angle and rotational geometry. The anomaly was small, almost trivial, yet multiple teams confirmed it. One astronomer suggested an unusually porous subsurface. Another proposed a composite core with materials of differing thermal inertia. But a few quiet voices wondered whether the lingering warmth indicated a delayed shutdown of internal outgassing, a final exhalation from an ancient reservoir sealed for billions of years. There was no consensus, only speculation, constrained by data fading faster each day. The strangest observations came from the dust modeling group. Their final reconstructions showed that the dust grains leaving the comet in the last phase were not distributed in a typical radial pattern. Instead, they formed a slightly asymmetric sheet, angled away from what should have been the primary direction of solar pressure. When the team attempted to resolve the anomaly, the models broke unless they introduced a brief, localized jet from a region no longer active. A jet that, according to the visible light instruments, did not exist. That discrepancy persisted in every revision. A few analysts joked about ghost activity, but no one could explain why the dust behaved as though the comet exhaled once more after every detectable sign of activity had ceased. A final mechanical shift, perhaps. Or something deeper within the nucleus that remained hidden even from our best instruments. As the days passed, the detections grew weaker. The last clear image came from Hubble, a faint smear against the starfield, barely distinguishable from background noise. After that, only the larger ground-based telescopes could trace its fading light. Eventually, those too lost it, and with that, the object slipped beyond the reach of human observation, a 10-billion-year-old traveler disappearing into a silence it had known long before our world existed. The scientific summaries were clinical, almost austere. They spoke of unprecedented carbon ratios, anomalous structural signatures, complex outgassing cycles, and a formation environment unlike any near our sun. But what stayed with me were the unanswered questions between those lines, the things the data suggested but did not confirm. Why did some readings appear briefly and vanish? Why did certain files undergo unexplained revisions before public release? Why did instruments at different vantage points disagree on structural features? And why did the dust behave as if the nucleus exhaled after its activity had already shut down? No one was willing to draw conclusions from such thin threads, but everyone felt the weight of them. In the end, 3i Atlas left us with more than chemical ratios and trajectory plots. It forced us to think differently, not just about comets, but about the environments that form them, the systems that eject them, and the ancient histories written into their icy cores. It revealed that our galaxy is not uniform, not predictable, and not bound by the narrow assumptions we carry from our own corner of space. Somewhere, billions of years ago, in a system long vanished or transformed beyond recognition, this object began its journey. It drifted through eras older than our planet, older than our sun, older than every species that has ever walked this earth. And by chance, or by the natural rhythm of the cosmos, it crossed paths with a civilization able to measure it for a brief moment before it vanished again. We didn't intercept it, we didn't sample it, we didn't unravel its origin, but we saw it. And in seeing it, we learned that our galaxy is far stranger, older, and more diverse than the models we once trusted. Now it is gone, a fading echo moving into the dark, carrying the last secrets of a star we will never know. The next visitor is out there already, somewhere in the vast silence, and when it arrives, I hope we are finally ready.